Now, we are looking at Rankine cycle today. Okay. Now, many of the impracticalities associated with the Carnot cycle, the previous lesson we did Carnot cycle, can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. So Carnot cycle actually possesses a lot of impracticalities, such as the turbine exit and the pump. Okay, so due to those impracticalities, we have to modify Carnot cycle. So then we have this, which we call Rankine cycle, which is the ideal cycle for vapor power plants. So the ideal Rankine cycles does not involve any internal irreversibilities, otherwise stated. Okay. So Rankine cycles. So many of the impracticalities associated with Carnot cycle. So we modified the Carnot cycle, so we got what we call a Rankine cycle. Okay, so this is basically a Rankine cycle, which you have 4 devices. One is boiler, then you have a steam turbine, condenser, and a feed pump. So water goes in. Before going into the boiler, you have heat supply to the water or to the saturated liquid or to the fluid that is going into the boiler, so that the pressure and temperature is brought up to the boiler inlet before it goes into the boiler. So, and in the boiler, it will undergo a constant pressure heat addition. In general, boiler is called a steam generator. So at the outlet of the boiler, usually the steam is either in a wet stage or as dry saturated. So usually, or most of the time, is dry saturated steam. Dry saturated steam, okay, before it goes into the steam turbine, where work is extracted to generate power and convert to electrical power. So in the steam turbine, the system or the working substance usually undergoes an isentropic expansion process. So during this isentropic expansion process, the entropy is constant, the pressure and temperature is brought down. Okay, so the pressure and temperature usually will drop to the condenser pressure. So the outlet from the steam turbine, usually it is in the form of mixture of liquid and vapor, or we call sometimes, most of the time we call it as wet vapor, or as dry saturated or superheated. It depends. Okay, so before it goes into the condenser, okay, the energy that is unwanted, that means the energy which cannot be converted to useful work by the turbine here, will go into the condenser, where it will undergo condensation, a condensation process. So a condenser works in different ways. So this is what we call a heat exchanger, where the heat from the hot steam will be transferred to the water that is going into the condenser, and then it goes out. So in the condenser, it will undergo constant pressure, again constant pressure, but then this time is constant pressure heat rejection. Constant pressure heat rejection. So then after that, it will go into the feed pump, where it undergoes isentropic compression. Isentropic compression, where the pressure and temperature will increase before heat is supplied by the burning of fuel. Okay, so basically, or in general, boiler, in the boiler you have constant pressure heat addition. In the steam turbine you have isentropic expansion where work is extracted or work output. Then in the condenser you have constant pressure heat rejection. And then in the feed pump you have isentropic compression where you have work input. Okay, so that is how the cycles works. So in clockwise direction again. So from state point 5 to 2, so this 5 to 2 here, okay, from this state point 5, that means the boiler inlet to the boiler exit here, okay, it undergoes a constant pressure process, or we call it as constant pressure heating from 5 to 2. Then from 2 to 3, you have isentropic expansion where work is extracted. Then from state point 3 to 4, that means from here to here, it will undergo another constant pressure process, but this time is cooling. Then lastly, you have the isentropic compression by the pump. This we call feed pump. This is a condenser. This is the steam turbine, and this is the boiler. So based on your TS diagram now, you can see 5 to 2 here, 5, 1, 2 here. This happens at constant pressure. Okay, and this pressure is called boiler pressure, the boiler pressure. Okay, so state point 1 is saturated liquid, since it is sitting at the saturated liquid line. State point 2 is dry saturated, since it is sitting on the dry saturated steam line or dry saturated vapor line. Then undergoes isentropic expansion 2 to 3, that is in the turbine. So work will be extracted from here. So, and you can see from 2 to 3, the temperature drop from this TH to the TL, or from the boiler pressure down to the condenser pressure. Okay, then from state point 3 to 4, you can see this happens at constant pressure process again, and it is called the condenser pressure. So during this time here, what happened is there is a change in phase, and then also for 1 to 2 here, also a change in phase. This is from liquid to vapor. This is from vapor to liquid, saturated liquid. Okay, so then from 4 to 5, you can see this line here is vertical, so that is isentropic compression. So work is supplied to the working substance in order to compress the working fluid so that the pressure will go up from the condenser pressure to the boiler pressure, and in addition the temperature also will increase before it goes into the boiler. Okay, so from this is called the Rankine cycle. Okay, this is called the simple Rankine cycle. That means the simplest form. Okay, so and when you look at this dashed line here, this is the original Carnot cycle where it is positioned. That means your point 4 somewhere around here is here. Okay, so what we did is we pulled the point 4 from this point that I shown in my using my laser pointer here. Okay, initially for Carnot cycle, the point 4 is here. Now it is being pulled until it reaches a saturated liquid condition. Okay, so this will give you an explanation where the condensation will complete. Okay, will complete when point 4 touches the saturated liquid line. So if let's say, for example, when you refers to point 4 for Carnot cycle here, my pointer, okay, actually, okay, the working substance is not completely condensed, which is impossible. So as we know that condensations always, once it starts, it will completely change back to liquid. There is no way of changing the working substance halfway where you have mixture of liquid and vapor when condensation takes place. Okay, so that gives you the explanation of the impracticalities of the Carnot cycle. The impracticalities of the Carnot cycle. Now, the next thing is, when we look into this Rankine cycle, there are 4 components, there are 4 devices here. All these 4 devices, they are categorized as the steady flow devices. So when we look into each device individually, we have to apply the steady flow energy equation. So first, let us start with steam turbine. So when we apply the steady flow energy equation for this isentropic expansion for the turbine, isentropic, the word isentropic means no heat flow, yeah? So based on steady flow, we have heat, work, specific heat, specific work. This is a specific potential energy. This is a specific kinetic energy. This is specific enthalpy. So based on this, we know that heat flow will be neglected. And then the potential and kinetic energy changes, if you were to refer back to what you have done in your previous thermal lessons. Okay, we know you will get to know that for turbine, the specific potential and the specific kinetic energy changes usually is neglected because it is negligible small. It will cause negligible effect to the energy related stuff in the equation. So therefore, that is why the specific potential and the specific kinetic energy changes take little effect only on the work done. So therefore, it is neglected. So what we have is only the work with the change of enthalpy from here. So this here will give you the explanation why we neglect each of the terms here. Isentropic expansion, so the process Q2 to 3 is being neglected. Negligible changes, that means very small changes for the specific potential energy, so it is being neglected. And then negligible change in kinetic energy, so the specific change in kinetic energy can be considered as very little also. So that is why it's again also being neglected. So you have only the work and the changes in enthalpy from here. So the negative sign, to deal with the negative sign, you can manipulate the H2 and H3 here so that you have H2 minus H3. So this is usually the work, output of the steam turbine, okay? So the next one is the condenser. So the condenser here works as a heat exchanger, okay? And it takes place during a constant pressure process. So a simple diagram which I have shown you here. So this is basically the inlet of the hot steam, and this part here is where you have your cooling water going in and coming out as warm water. So this will help to convert the saturated vapor or wet vapor at the condenser inlet to saturated liquid. This is the most important thing. It must go completely condensed, okay, before it goes into the boiler, or before, okay, it enters the pump. Actually, before it enters the pump, because pump can only deal with one phase, single phase, that is liquid. So if there is a mixture of liquid and vapor, the pump will burn out. So make sure 0.4 sits on the saturated liquid line. So now, again, based on steady flow, now this time we have 3 to 4. So basically, there is no shaft operated in condensers. So the work usually is neglect, potential kinetic energy all being neglected. Okay, so it is stated here. So what you have is the heat rejected is equals to the change of enthalpy. Then the next one is the feed pump. Okay, feed pump will undergoes isentropic compression. Work is supplied to the pump in order to compress the substance to higher pressure and higher temperature. So based on the steady flow energy equation, again, pump is also a steady flow devices. So based on isentropic compression, so you have this equation between 4 to 5. So this case here, since it's isentropic, heat is neglected, potential neglected, kinetic energy, specific kinetic energy neglected. So what you have is the work with the change in enthalpy once again. Okay, so these are the 3 points why or when. Okay, these terms can be neglected. So this is work input and it is equals to the change of enthalpy. Then the next and the last, that is the boiler. Okay, so it happens during constant pressure process again, and it is called a steam generator. So going in as saturated liquid from the pump exit and burning start to take place. That means you need to burn fuel like charcoal, oil, gas, and etc. in order to, okay, change the phase of the substance from liquid to hot steam. So in the stage of hot steam, okay, you have quite an amount of energy stored inside the working substance or the system. And so at least coming out as wet vapor or dry saturated vapor or steam. So boiler is dealing with heat, so can't neglect the heat, but boiler doesn't need or doesn't require a shaft in order for it to operate. So the work can be neglected. Change in kinetic and change in potential energy also can be neglected. So from here, work is neglected. And then the specific potential energy is neglected. Change in kinetic energy is also being neglected. So you have only the heat supply with the change of enthalpy. So basically from what we have gone through just now, basically if let's say for example we want to find heat rejected, heat supply, work output, work input in general, we can say all these are actually equal only to the changes in their enthalpies. Okay, so what you need to do is to obtain H1 to H5 from your property tables. Later on, I will show you quite a number of examples. Okay, working problems. So ways of increasing the thermal efficiency of a Rankine cycle. So basically, Rankine cycle, okay, has a very low thermal efficiency. Okay, so in order to increase its thermal efficiency, now first point is what you can do is by lowering the condenser pressure. I hope by now you know which one is the condenser pressure. Lowering the operating pressure of the condenser automatically lower the temperature of the steam. Second point is by superheating the steam to higher temperature at the boiler exit. So every time or most of the time when the steam comes out from the boiler, it is being sent back to the boiler again for superheating. Superheating it to higher temperature. Okay, that is the second point, how to improve the thermal efficiency. The third point is by increasing the boiler pressure. That means bring the upper pressure limit, that means that is the boiler pressure, to a higher position, or to bring the condenser to a lower position. So that means it opens up the gap in between the boiler pressure and the condenser pressure. So the larger the difference, that means the greater will be the work output actually. So the greater the work output, that means the thermal efficiency will be increased. Okay, that's in general. So the second part have superheating. So we are looking at superheating. So a superheat Rankine cycle. Superheats improve quality of steam at turbine exit. So if we just leave it as dry saturated at the turbine inlet, what happens is at the turbine exit, the quality of steam from the exit will be very low. That is somewhere around 0.6 to 0.7. That is what we don't want. We want dryness fraction or the quality of steam at least 0.9 and above. So actually by superheating itself is not enough to improve the quality of the steam. Okay, so superheat improves quality of steam. It improves, but it doesn't bring it over x equals to 0.9 and above. Okay, at turbine exit as well as improvement to the efficiency. Superheating at too high temperature in order to remove excessive moisture content at the turbine exit becomes very impractical due to metallurgical limits, because the materials that we use to build up the boilers, they have a temperature limit. So we cannot, most of the time, we cannot say, okay, we want to superheat the the steam up to above 650 degrees C. Okay, due to metallurgical limits, certain material cannot reach above that 650. Okay, so that is one limitation. Okay, so that is why from superheat it brings us to reheat later on. So this is basically the superheat Rankine cycle. When the steam comes up from the boiler, so remember in the boiler it undergoes constant pressure heating. So when it comes up, usually it's in the form of wet vapor or dry saturated vapor only. So what we do is we send it back to the boiler for superheating. That means heating it to higher temperature, but not too high, but then up to a certain temperature limit only. Okay, so that is due to this limit here. So then after that, it goes into the steam turbine. Okay, it goes into the steam turbine where it undergoes isentropic expansion. Okay, after isentropic expansion, okay, it goes into the condenser where it undergoes constant pressure cooling or heat rejection. Then it goes back to the pump where it undergoes constant pressure compression, isentropic compression, not constant pressure, isentropic compression. For condenser is constant pressure cooling, isentropic compression to bring up the pressure and temperature, then goes into the boiler and heating process takes place, and the boiler generates steam at constant pressure, like that. Okay, so that will complete the cycle. Okay, so process 1 to 2, okay, that means from here to here, reversible adiabatic expansion in the steam. Then you have process 2 to 3, that is constant pressure, okay, constant pressure cooling. That is in the condenser. Then you have the isentropic compression in the pump. Okay, then you have, isentropic compression in the pump, constant pressure, okay, cooling in the condenser, so it converts a vapor or steam back to liquid. Then to the pump, you have isentropic compression, raising the pressure and temperature, and then in the boiler, constant pressure again, okay, heating. So heat supply here, heat rejected here, work out here, and work in here. Work in is here. So this is work out based on this device. Based on this, you have heat rejection. Or based on this device, you have work input. And based on this device, you have heat supply. Okay, so this is your TS diagram. So you can see this is your constant pressure heating 4561. So this is constant pressure heating. So from 0.6 here, from 0.6, the steam actually sent back to the boiler before going into the turbine. Sent back to the boiler where it undergoes superheating process and heating it up to a superheated temperature. This one is higher, yeah. Superheated temperature at 0.1. Then after that, it will undergoes isentropic expansion to 0.2. Can see it's roughly around x equals to 0.7 or 0.7 something. Okay, so that means the quality of steam is not properly improved yet. So it is coming up still as wet vapor with low dryness fraction, low quality. So remember this superheated line here, this temperature line here should be shifted so that it touches 0.1. So this is my mistake here, error. So then 0.2 to 3 is where you have your constant pressure cooling. Then 3 to 4 is isentropic again. Isentropic here, constant pressure and constant pressure here. So this is heating, this is cooling, this is work output, and this is work input. So state 0.1 here is superheated. So how to find the superheated? It's actually H1 equals to, not Hg, the H, not Hg here. Okay, the H, go on. Let me delete this. There is a problem with PowerPoint sometimes. This one, there's no G here. Okay, so H1 is actually H1 equals to H. Is actually H1 equals to H at the superheated temperature. So you can find it from the property tables. I will show you in the example. Okay, so and then S1, so you have to make use of this. Yeah, so 0.1 to 2 here is an isentropic process. So therefore you can say S1 equals to S2. So from H1 you can go up to H2 by finding out the dryness fraction based on the difference, okay, in the entropy of S1 with the actual S2. Okay, so you can find out the dryness fraction. Okay, so S1 equals to S2. There's a mistake here again. Okay, so based on S1 equals to S2, actually you can use this equation to find out the dryness fraction. So this is the dryness fraction. Then once you have found out the dryness fraction, you can put it into the enthalpy formula. HF is your saturated liquid enthalpy, multiplied by the dryness fraction you have found with the HFG. Actually, in the table, most of the time they give you HFG. So in case they don't, so you can take Hg minus HF. Then state 0.3 that is here. And this is sitting at the saturated liquid line. Sitting at the saturated liquid line. So you can straight away take H3 is actually equals to HF at the condenser pressure. This is the condenser pressure. Then H4, it is the compressed liquid. So in order to find H4, there are multiple ways. One of the ways is, we know that work input here is H4 minus H3. Is H4 minus H3. So we can find out H4, okay, by taking H3 plus 0.001 times boiler pressure minus condenser pressure. Okay, H4, not the work in. The work in should be equals to H4 minus H3. So the heat supply okay, we can take H1 minus H4. Once we have found out H1, H2, H3, and H4 or H5. Okay, so you have the heat supply, you have the work output, hold on, you have the work output, the heat rejected, and the work input. Okay, that's for superheat Rankine cycle. That's for this section. Okay, reheating, part 3. So reheating is actually to further improve the thermal efficiency and also the quality of the steam at the turbine exit. That is the major thing that we are looking at usually. Okay, how to improve the quality of the steam at the turbine exit, and then how to improve the thermal efficiency and so by reheating, by reheating Rankine cycle, actually you can achieve that 2 points. So reheat Rankine cycle. The reheat Rankine cycle further improves the quality of the steam at the turbine exit, remove excessive moisture, and also improve the cycle efficiency slightly, and it relies on the number of stages of reheat. Okay, you can go to a number of reheat stages, but every reheat you need a turbine. You will have an extra turbine. So every reheating process, one reheat, you have 2 turbines. Two reheats, you have 3. Okay, 3 reheats, you have 4. So you will keep on increasing the number of turbines, which is not economical also, which is non-economical. So basically that is your reheating cycle. So first, superheat. So coming out from the boiler, is usually dry or wet, then send it back into the boiler for superheating first, then go back to the steam turbine where it undergoes isentropic expansion on the first turbine, which is called the high pressure turbine. Then it goes back to the boiler for reheating. So it comes out as reheated steam. Okay, usually is superheated. So it goes into the second turbine where it again undergo an isentropic expansion based on the low pressure turbine. So you have 2 turbines, one is called high pressure, the other one is low. After the low pressure turbine, then only it goes into the condenser where those unavailable energy, means the energy which we cannot convert it to useful work, the energy will be rejected. Okay, our cooling process will take place here, or the saturated vapor or the wet vapor will be condensed until it becomes saturated liquid, then goes into the pump where it undergoes isentropic compression to higher boiler pressure and temperature. That means to the boiler pressure and boiler temperature. Then it is again sent out and then complete the cycle. So basically, in general, heat supply here from the boiler, work out from the high pressure turbine, then you have work out from the low pressure turbine. So that means you have work out based on this and this. Then you have heat rejected based on the condenser, work input based on the pump. So the heat supply, you can take H1, no need the 7. We go straight away H1 minus H6 for heat supply. Okay, H1 minus H6. Work output H2 minus H1. Work output from the low pressure turbine H4 minus H3. So the total work output, you can say H2 minus H1 plus H4 minus H3. Heat rejected will be H4 minus H5. Work input will be H6 minus H5. Okay? So 1 to 2 isentropic expansion for the high pressure turbine. 2 to 3 is constant pressure reheat. This is a reheating. So you have heat supply in addition here also, yeah. Here also you have heat supply. Okay, so heat supply you have based on H1 minus H6 and H3 minus H2 as well. Then you have another isentropic expansion, that means another work output based on the low pressure turbine. Then you have heat rejected based on the condenser where it undergoes constant pressure cooling. Then you have isentropic compression 5 to 6 where you have your work input. Then 6 to 1 constant pressure heating, that is the boiler, 6 to 1 straight away. Okay, so that is your TS diagram. So the superheated temperature is here. So usually it is superheated at 0.1 and reheat at 0.3, which is back to the original superheated temperature. That means back to the H1 temperature, or the superheated temperature at 0.1 and 0.3 should be the same. Otherwise will be mentioned, will be stated. Okay, so from here, H5, or you can take H6 to H1, this is your boiler. Your boiler actually 56781. Sorry, 56 is pump, 6781 is your heat supply, plus 2 to 3 is also your heat supply. So if you want to find the heat supply, you can straight away take H1 minus H6 plus H3 minus H2. You have to analyze, you must know how to read the TS diagram. Then work output, you can take H1 minus H2 plus H3 minus H4. Okay, so you have two isentropic expansion here. Then heat rejected, you can take H4 minus H5, which is at constant pressure. We don't call it a constant temperature here anymore, yeah, because here is on the constant pressure line, 4 to 5. Then 5 to 6 is where you can find your work in by taking H6 minus H5. Heat supply, I repeat again, total heat supply is H1 minus H6 plus H3 minus H2. Total work out is H1 minus H2 plus H3 minus H4. To find the thermal efficiency or the cycle efficiency, all the same. Net work out over heat supply. That means the desired out over the total desired out divided by the total required in. Okay, so I have written here the heat supply 6 to 1, 2 to 3. So total heat supply. Then you have work out 1 to 2 and work out 3 to 4. So that will give you a total work out. Okay, the work in is 6 to 5. So H6 minus H5, heat rejected is H4 minus H5, like that. Okay, that's for reheat Rankine cycle. So the next part is the regenerative Rankine cycle. So regenerative Rankine cycle. The regeneration process in a steam power plant is accomplished by extracting or bleeding steam from the turbine at various points here. Okay, this steam, which could have produced more work by expanding further in the turbine, is used to heat the feed water instead. The feed water, this device here is called an open feed water heater, which is a mixer, which it undergoes an adiabatic mixing process. Okay, an adiabatic mixing process where it mixes the blade steam with, okay, the saturated liquid here. it mixes the blade steam. That means the steam which before it undergoes full expansion, so at certain points here, you can pull out, okay, or we call it as blade steam. You can pull out a certain amount of hot steam to heat up the saturated liquid from the pump before you send it to the boiler. Actually, you can reduce the amount of burning fuel. Okay, so the device where the feed water is heated by the regeneration is called a regenerator or a feed water heater. So in this case, we are looking at open feed water heater. So the optimum number of open feed water heater is determined from economical considerations. Many large plants use as many as 8 open feed water heater, 8 of these. Okay, 8 of this. So from here, from the diagram, you can see this is a boiler where you have constant pressure heating. Then the steam that came out from the boiler either is wet or dry saturated or superheat, either of this, point 1. Then it goes into first turbine. If let's say you have only one turbine, you can have a number of turbines. You can have 2, 3 turbines for reheating plus regenerative. Okay, so it becomes tedious. Okay, as more turbine you put in, more open feed water, okay, the whole process becomes much tedious. So before it undergoes a full isentropic expansion, certain amount of steam is extracted. Let's say X kg. Let's say X kg. So this hot steam that is extracted or pulled out from the turbine goes into a mixing chamber, or we call regenerator, which is also known as open feed water heater. It mixes with another stream of substance that is your saturated liquid or saturated water. When it mixes, it actually increases its pressure, bring up its pressure slightly, and also temperature. So then only it goes into the last pump before it goes into the boiler. So indirectly, okay, what happened is the amount of burning fuel that is required is reduced. Okay, so constant pressure heating, isentropic expansion, work output, constant pressure cooling, heat rejection, work input, and work input. But usually when we go to regen and reheat, we neglect feed pump work. We don't have to consider feed pump work. If you want to consider, can. But if you want to ignore or neglect it, also can. You get what I mean? The difference doesn't make, it doesn't make a difference or a large difference. Okay, you neglect or you don't neglect. But most of the time we neglect because we save out the calculation work. Okay, so this is a TS diagram. Okay, so we start from point 1. In this case, dry saturated. This is your dry saturated vapor line. That is the G line. So any properties here on this line is referring to a subscript G because it's dry saturated. So dry saturated at point 1. So it undergoes isentropic expansion to point 2, where a certain amount of steam is extracted. So let's say initially is 1 kg, example, 1 kg. So at point 2 here, a certain amount of steam is extracted. So let's say X kg. So the remainder here should be 1 minus X kg. And here also must be 1 minus X kg. So your turbine work, you have H1 minus H2. But times it with 1 kg. Then you have work output based on the second stage here, that means the remainder from 2 to 3, you take 1 minus x based on this, multiplied by H2 minus H3 for the work output. So basically your work output will be 1 kg times H1 minus H2, and then 1 minus x kg H2 minus H3. Then your heat rejected will be H3 minus H4, work input will be H5 minus H4, and H7 minus H6. So if we neglect this and this, you just cover off this part, okay? If you just cover off this part, okay, your heat supply will be H1 minus H6 straight away. That means H1 minus H6. Here you have no heat supply. Here you have exchange of heat between the blade steam and the saturated liquid to form something wet vapor or dry vapor, wet vapor or saturated liquid. Okay, so this is a mixer. So it's not considered that heat supply, you got heat supply from here. So the boiler, constant pressure heat supply, isentropic work output expansion, constant pressure cooling. Okay. So I've shown you in different type of colors of arrows, shows that each stage of the working substance. So that is how it works. Okay, you extract, remainder go here, go down to condenser, pump. The pump will increase the pressure and temperature here from 4 to 5 here, you can see, to go into the open feed water heater to mix with the stream from point 2 at 6. So 6 to 7 is isentropic compression, 6 to 7. Then from 7, 8, 1 is where you have your heat supply. If you neglect your feed pump work, that means you don't want to consider feed pump. So your heat supply, you can straight away take H1 minus H6. And then I repeat once more, work output here is H1 minus H2 times 1 kg. That means your absolute work here. Then you have H2 minus H3 times 1 minus x kg here. Okay, so I have listed everything here for you. This is heat rejected, that is based on 1 minus x. So everything you get from this will be absolute because you are taking the mass of the working substance or the steam into considerations. Okay, so and this is your work output. So what you have, the unit that you use here will be in kJ. This will be in kJ. This one, if you multiply by 1 here also, it will be in kJ, kilojoules. Okay, that's what you need to remember. Work in usually we neglect for any reheat or regen. Okay, that's all for Rankine cycle. So when you go for higher level, let's say degree and so on, you will have more stuff, like let's say for example you can combine regen and reheat, okay, and then maybe you can have combined heat power, then you might have combined of geothermal energy with a steam power plant, and etc. etc. You have a lot of modification to it. Okay, so I will publish all these working problems based on combined heat power, based on combined regen and reheat in the YouTube for you to view, for you to understand how the things work before you go for your higher level. Okay, thank you very much. Stay safe, and I will see you all in the next lesson. Oh, sorry, before we move on, before I say that's all, there is another part that is based on the open feed water heater, which I have left out. Hold on, sorry for that. Okay, so this is based on the open feed water heater. Okay, an open direct contact feed water heater is basically a mixing chamber where the steam is extracted from the turbine mixes with the feed water exiting the pump. Okay, ideally the mixture leaves the heater as a saturated liquid at the heater pressure. So here usually is saturated liquid. So here you have blade steam, the steam that you take up from the turbine. Here you have the compressed liquid, okay, of the liquid from the pump, okay. So this is a mixture, a mixer or a regenerator. So based on energy balance and mass balance, okay, based on energy balance first, okay, these two are in and this is out, okay. So H2 and H5 here I use absolute because I take into consideration, after I will take consideration into the mass of the substance. So H2 here, this line here, you have x kg. So that is why I multiply this by, okay, x kg or mass M2. Here mass M2. Okay, here this is H2. And here you have mass M5. I put M5 mixed with H5. H5 with M5. And then M6, sorry, M6 with H6. Okay. Then M2 is actually X. M5 is actually 1 minus X. And then M6 is actually 1. Okay, so this is your energy balance and mass balance. Okay, that is the continuity equation plus your energy balance equation. So from this, if you look properly, when you manipulate this, okay, or simplify this equation, you will arrive to something like this. That means removing all the units. It looks tedious with all the units, okay? So just remove all the units. Okay, so you will have this equation here. So when you manipulate and put x, any quantity that is with the x beside it, onto the left hand side and those without on the right hand side, then when you manipulate, actually you can find out based on the enthalpies. So that means that you have to first find out all the enthalpy first before you can find out how much of steam you can remove from the turbine to run this process. Okay, that's all. Thank you. This time is really thank you. And stay safe until the next lesson. Okay, bye bye.